Alright, welcome back to the second video. So in the first video, we have mentioned about this idea of enthalpy change and what is the idea of Hess law. And in fact, we went on to talk a bit about enthalpy change of formation as well as the enthalpy change of combustion. So in this particular video, I will just focus on enthalpy change of neutralization as well as this idea of calorimeter before we go on further to the next video where we will zoom in into the other types of enthalpy changes. So, what exactly is the meaning of standard enthalpy change of neutralization? As the name suggests, this is about looking at the energy involved when we are looking at a process of neutralization. So we know that neutralization is a reaction between an acid and a base, right? Nothing new from what you have learned. And when you talk about standard enthalpy change, we are looking at when 1 mole of water is produced under standard conditions, right? So this is what we term as standard enthalpy change of neutralization. Just like what you have learned in your O-level syllabus, this is an exothermic reaction. We know that neutralization is a reaction that releases heat to surrounding. The test tube or conical flask will feel warmer as the neutralization is happening. So, an additional information to take note over here is that in the syllabus itself, you will grow to realize that actually the standard enthalpy change for most of the strong acid and strong bases, right, is always constant at negative 57 kilojoules per mole. This will be the energy released when strong acid and strong bases react together. But what about weak acid and weak bases? So in our O-level syllabus, right, we learned that strong acid and strong bases, they ionizes completely, or we say that they dissociate completely in the solution to release either H plus ions or OH minus ions. So because strong acids and strong bases, right, they have this complete dissociation when they are in a solution state. This actually allows all the H plus and all the OH minus to react together, and hence the energy value that we're looking at is always constant because we are essentially looking at the same amount of H plus and OH minus coming together to form 1 mole of water molecules. But when you have weak acids and weak bases, right, that is a different case because they do not ionize completely. So one example would be if you look at something called ethanoic acid. This is an example of a weak acid. So when it's placed inside a solution, what happens is that you will see this reversible arrow and it will be a partial dissociation. So similar to what you have learned in your O-level syllabus, right? So it's a partial dissociation because they do not ionize completely. And as a result, what happens is that during the whole neutralization process, where we still want the H plus and OH minus to react together, you need additional energy to help to ionize the unionized weak acid. That means when this is in a solution, there will be a bit of H plus, but not all the H plus will be released from the compound over here. So what must you do to allow this H plus to come out? You actually need to involve energy to help you to further dissociate these so that all of them can become H plus. And when we do that, what it means is that when energy is absorbed, right, there is actually an endothermic process. So if you recall, by right enthalpy change of neutralization for strong acid and strong bases, you are looking at negative 57 kilojoules per mole, right? But if for weak acid and weak bases, you need to take in some energy to help with the ionization process, then you will expect this to be less than, rather a less exothermic process for the case of weak acid and weak bases. And hence you see a top line in your notes over here that the energy is actually lower. Yep. And so with that, just need to take note that the value of negative 57 kilojoules per mole only applies to when there's a reaction between a strong acid and strong base. But when it comes to a weak acid and weak base, we expect the value to be less exothermic. So for example, negative 30 kilojoules per mole, so on and so forth. And so for the next few slides, you can see some examples to show you how the calculation is like. We won't go through it in key details. Alright, so now I'm actually going to talk about this idea of calorimetry, right? So calorimetry actually came from this term called calorimeter, right? So calorimeter is this setup that you see over here in this screen, right? It's basically a setup to help us to actually find out the amount of heat that is being evolved or the amount of heat change, right, that happens when a reaction takes place. And through that, that actually allows us to calculate enthalpy changes. So if you recall, enthalpy change is essentially a calculation of energy per mole of a reaction, right? So hence the unit for enthalpy change is always in terms of kJ per mole, right? So you look at the amount of energy per mole of a particular reaction, be it formation, neutralization, or combustion, etc. So what a calorimeter helps us to do is that it actually allows us to find out what is this amount of energy that is coming out from the reaction, and then we use a mathematical calculation to divide it by the amount of mole, then you'll get enthalpy change. So this equation that we'll be using now is actually this formula that you see over here, Q equals to mc delta T, right? Delta T stands for the change in temperature, so I'm just going to highlight as we go along. Change in temperature. Assuming that this reaction releases heat to the surrounding, the thermometer will register an increase in temperature, right? So the increase in temperature will be so-called the change in temperature. Q refers to the heat change, right? The total amount of energy that is being released or taken in depending on the kind of reaction that we're looking at. M refers to the mass of the solution. And last but not least, C actually refers to this thing called specific heat capacity of solution. Now, those of us who don't take physics here, this symbol of C, specific heat capacity, may be a bit new to you, but not to worry. In terms of the concept-wise, it's actually pretty straightforward. So before we go on back to the notes, let's take a look at a video which summarizes quite well about the concept of calorimeter.
In this video, we are going to learn about calorimeters, what they are, how they might be used, and why they are used. A calorimeter is a device used for calorimetry, the process of measuring the change in heat of chemical reactions, or physical changes, as well as heat capacity for a material. When you look at food items, their energy content was worked out by burning the food in oxygen to see how much energy is released. This corresponds to the energy content label and is given in calories. To do this, you have to use a calorimeter. The simplest calorimeter consists of a thermometer attached to a metal container full of water and is suspended above a combustion chamber. In a typical calorimetry experiment, you can measure the energy that is released from fuels. Can you think why this might be important? The answer is that different fuels release different amounts of energy. So if you're flying a plane, you need a fuel which releases more energy than say if you were driving a car. This is because the plane is heavier than the car, so more energy is needed to make it move. In the classroom, if you do this experiment, you would do it on a much smaller scale, using a spirit burner. This is what you would need to do. 1. You'd measure the mass of the spirit burner before the experiment. 2. Add a certain amount of cold water into a copper calorimeter, a small metal can, and suspend it at a fixed distance from the spirit burner. Can you think why it is important for it not to be too far away? Pause the video and continue when ready. The answer is that in this sort of experiment, a lot of the heat is transferred to the surroundings, so you need to minimise this by either placing the spirit burner as close to the calorimeter as possible, or you could reduce this by insulating the sides and adding a lid. 3. You'd measure the starting temperature of the cold water. 4. You'd use the spirit burner to heat the water for a fixed amount of time. 5. Record the mass of the burner afterwards so that you could calculate the mass of the fuel combusted. And finally 6. Record the temperature change of the water caused by her heating. Can you think why you might do the experiment more than once? Pause the video and continue when ready. The correct answer is that you want your results to be as accurate as possible. This also improves the reliability of the results you collect. If you have a larger temperature change on doing this experiment with one type of fuel than another, this means that more heat energy was transferred to the water than if you have a smaller temperature change. The best fuel is likely to release more energy per gram of fuel. In summary, calorimeters are devices that can measure the heat of chemical reactions, physical changes, or heat capacities for different materials. A simple experiment showed how measuring the temperature change of water could be used for this purpose. The larger the temperature change per gram of fuel, the more energy released.
Alright, so as briefly mentioned within the video itself, right, in the whole set of calorimeter, especially in the school lab, we tend to use a polystyrene or styrofoam cup because this styrofoam cup is a good insulator so as to reduce the amount of heat that's lost from the side, trying to minimize all these things. So if you recall, right, actually for those of you who are taking your chemistry practical practices as well as for the preparation for O-level, you realize that a lot of the energy change reactions that you do in the lab, we also use a polystyrene cup, right? So a styrofoam cup, and that is really because of this idea of how you want to minimize heat loss so that your results, the temperature change that you are measuring, can be as accurate as possible. We also add a lid. So a lid is useful to minimize the possible sources of error, which is the heat loss that may happen. Okay, so and of course we use a glass beaker to support and to hold the styrofoam cup by itself. So some of the assumptions that we use when you talk about calorimeter, which also applies to your current chapter on energy changes, we actually assume that there is minimum amount of heat loss or heat gain from the surrounding air, because if not, it's almost impossible for you to calculate your values in terms of the heat change, right? Because you know that there will always be heat loss, so that's a source of error. But in terms of the calculation, we just assume that there's no heat loss or heat gain. Next, we also assume that the heat capacity, right, of that material that's used to make the calorimeter, right, is negligible, right? So unless the question gives you the heat capacity of the material itself, there's no need for you to include it in when you are calculating the heat change, right? So we assume that it is not significant in the whole calculation. So we just focus on the heat capacity of the reaction mixture, which in this case is the solution. So how does this work out? So just like what was mentioned in the video, we're going to take a look at an example here to see how do we then apply this whole idea of calorimeter to help us with the calculation of enthalpy change. So in this example over here, we are looking at the reaction between HCl as well as NaOH. So this is your typical acid and base reaction, a neutralization reaction. And in fact, this is the strong acid, this is a strong base. So even without doing the whole calculation, I should be expecting to see perhaps an enthalpy change of neutralization of, say, about negative 57 kilojoules per mole, right? But of course, this is a theoretical value, right? So this is on paper, this should be what we determine. But it doesn't mean that in an experiment, because you're collecting actual data, right, you may not actually end up with this exact value, and that's fine, right? Because experimental data and theoretical data can differ, right? Because we know that it's impossible to ensure that there is really zero heat loss or heat gain. Okay, so it's not possible for you to always get the theoretical value. So based on this data that's given over here, the reaction involves a temperature change, right? So they mentioned about how they look at the initial temperature of the two solutions, then the highest temperature that's reached, right? So what we're going to do over here is that we're going to apply the formula that was shown in the earlier slide as well as in the video, whereby we look at the amount of heat evolved by following this formula of Q, which is heat equivalent to mass times specific heat capacity of the solution times delta T. Delta T represents temperature change. Okay, so the temperature change that we're looking at here is essentially this brown highlight. This is our temperature change, right? Because we know that the highest temperature is 34.6 and the average of the starting temperature is 22.4. Okay, so we look at the initial temp. Then the specific heat capacity. Now, because we are using something that's mainly a solution by itself, right? So a solution would comprise mainly of water, because water is used to dissolve the solids inside. So this C specific heat capacity, right, we can actually take the value of the specific heat capacity of water, which is 4.18, right? So actually this allows us to do that calculation. Now the mass, okay, because we are using 40 cm3 of the acid with 50 cm3 of the alkaline, the mass is actually calculated by assuming that it is largely the density of water, which is 1 gram per cm3. So 90 grams would be equivalent to, actually, you just be equivalent to 90 grams. So 90 cm3 would be equivalent to 90 grams based on the density of 1 gram per cm3 for water. Right, so we end up all these things together, you calculate, you end up with your value of Q, which is the heat change that is evolved. Right, so then you end up with this value of 4590 joules. Now this is the value of heat change. This is not enthalpy change, right? Because enthalpy change is actually equivalent to heat change divided by the mole, right? The mole of the reaction, whether there's a limiting reactor and whatnot. So when you look at the next slide now, we're trying to calculate enthalpy change. So enthalpy change, in terms of the formula, should be equivalent to the heat change divided by the mole of the product that's being formed, right? So in this case, how do you know how much product is being formed? We have some values in terms of the reactants, right? So you have a 40 cm3 of 2 mole per dm3 of HCl. You also have a 50 cm3 of 2 mole per dm3 of NaOH. So you can do your typical mole calculation to find out what is the molarity that's being involved over here. And of course, given that there's two sets of values being given, you do need to take note of which is the limiting reactant. And based on the calculation over here, HCl is a limiting reactant. So the amount of water that's being formed will depend on the amount of HCl that's present, and this gives us the results of 0.08 mole. Right, you can look through a calculation yourself to see if it aligns to what you have already known in terms of chemical calculation concepts. So NW change of neutralization then, in this case, will be equivalent to taking the heat change divided by the molarity, and you end up with this value of negative 57.4 kilojoules per mole. So see what I mean by the value that you get over here. Okay, over here you get a very nice value, but it need not always be the case, because in an experiment itself, the data that you collect, there may be some difference from the theoretical value that you're looking at. Okay, so but this is still pretty close to the value that we are expecting, right? So this is an example of how the calorimeter actually allows us to track the temperature change. Then using the formula itself, we can calculate the enthalpy change. So just another example before we end off the video, right? So if you are now asked to find the enthalpy change of combustion, which is, if you recall, the amount of heat that's evolved when 1 mole of a substance is completely combusted in excess oxygen, of course under standard conditions, so on and so forth. So how do we do that to know that the combustion itself, how much heat does it generate? So we actually burn the fuel, right? Depending on what's the molarity that's given. Burn the fuel, allow the heat to be transferred to the calorimeter. Right? So in this case, you're using a copper calorimeter, and allow it to warm the water that's inside. So what happens here is that the heat that's being transferred here, I'll use Q to represent, is then being used to heat up the water in the calorimeter. So how do you know how much heat is there? We actually look at the mass of the water. Okay, this is just like just now in the previous example, we look at the mass of the solution, right? In this case, I'm heating the water, right? So the mass of water is important to me. I'll multiply by the specific heat capacity of water. And then based on the energy change, I will look at the delta T, which is the temperature change itself. Right, so all this will allow me to then apply the same set of formula, but this time around is specific to the reaction between the fuel and the excess oxygen. So these are my combustion reaction. Right, just now was the neutralization, whereby the acid and alkaline are reacting together. So using the same method, you can then calculate the enthalpy change by taking the heat evolved divided by molarity. Right, so this slide itself just shows you how to calculate the heat that's being evolved, right, using the same formula that I mentioned just now, Q equals to MC delta T. Then to find out the enthalpy, we take Q divided by N, right? So this itself is how we use the methods. So how do you know the mole? This time around, the mole, we look at the mass of the chemical that is being reacted, because it's just about combusting the chemical, right? So if you know that 0.53 gram is being combusted, you take mass over mR. That will give you the mole of the chemical that is being used up, right? Then you do the calculation and you should be able to end up with these cell values.